Hello, this is the first lecture for this week, covering two of the really major hormones, thyroid hormones and cortisol primarily from the adrenal cortex. So you have your releasing hormones from the hypothalamus. They stimulate the anterior pituitary to release thyroid stimulating hormone and adrenal cortex stimulating hormone, ACTH. And then those glands in turn send out thyroid hormones and the adrenal hormones, mainly cortisol. So we're going to spend a lot of time with the thyroid gland. We're not going to get that in depth to the others, and that's because this is a kind of overall view of how hormones are produced and how they're transported and how the this and how the that. And therefore, when we hit the other ones, we'll just say, oh, well, this one acts, is transported kind of like thyroid hormone, which the steroids are, or it's not, which all the other ones are. So we won't spend as much time on the other ones as on thyroid hormone. So don't panic because there's so much on this. The thyroid is in the on the throat, just around your Adam's apple, just below your Adam's apple, if you can feel that. And if you had a swollen thyroid gland, that's called a goiter, and you could palpate that. You could feel it on either side, and it can get really big, but even somebody with just a little bit of hypothyroidism is likely to have a thyroid gland that can be palpated, that you can actually feel. So what this it has a bunch of these cuboidal cells that secrete. First of all, they secrete colloid, which is a precursor to your thyroid hormones, and the cells are wrapped in around little balls, and they secrete this colloid into the cell itself, into this ball of cells, a hole in the middle. It processes that stuff into your thyroid hormones, and then it takes it back out again. So the colloid is a juice that contains thyroglobulin, and a globulin is just a large molecule capable of producing thyroid hormone. So here we have the thyroid gland, right below your Adam's apple here. It's going to secrete your thyroid hormones, which are T4 and T3 and RT3, which we'll talk about in a few minutes here. Here you have the cells. Here, these are little capillaries going around them. So these cells are going to take what they need from the capillaries and secrete this colloid with the thyroglobulin into here. And this will store it until they need to take it back out to make thyroid hormone out of it and then release it back into the bloodstream. Now, your thyroid hormones are T4 and T3 primarily. T4 is thyroxine. Thyroxine is T4. T4 is thyroxine. So when we say thyroxine, no, this is the one we're talking about. Your thyroid gland mostly makes T4, thyroxine. It's also called tetraiodothyronine because it has 4 iodines on it. Tetra means 4. You also make T3, which is triiodothyronine. It has 3 iodines on it. Now, T3, you make a little bit of that in your thyroid gland, but mostly after the thyroxine gets inside the target cell, the cells have a way of converting T4 to T3 because it's a lot stronger. So to get the best action out of your thyroxine, you'll transport it through the blood, it'll go inside the cell, you'll convert it to T3, and then it can have its effect inside the cell. So mostly T4, a little bit of T3, and then you also make what's called reversed T3. Reverse T3 is a version of these that is inactive, and we'll talk about that, because if you need more thyroid hormone, you take your T4 and convert it into T3. If you need less thyroid action, you convert it into RT3, which is inactive, and you'll excrete it eventually and pee it out. this will make it kind of clear. It doesn't look clear when you first look at it, but what you do is you take tyrosine, an amino acid, and you put two of them together, and you stick iodines on it, and presto, you have tetraiodothyronine. Thyroxine, or T4, has 4 iodines on it. T3 has 3 of them. Okay? RT3 has 3, but they're in the wrong place, so it doesn't work. So T4, T3, RT3. Iodine, as you can see, is critical. You can't make your thyroid hormones without iodine. And iodine it's an essential element. You don't make it, you have to eat it. It's the only way to get it, really, is to eat it. And we have iodized salt, and we eat a lot of salt in the Western diets, and our food has generally plenty of iodine in it if we have any kind of a varied diet at all. But early in the times of the U.S., when you didn't have iodized salt at all you were eating was lean meat and vegetables, you were likely not to get enough iodine. And still in developing countries, landlocked countries, iodine comes from the sea. And so if you are close to the ocean, or if you live on land that used to be under the sea, there's enough iodine in the soil that you get it in your vegetables you eat. So if you find somebody, a test question that says something like Central South America, village in Central South America, village in Central Africa, far away from the ocean, that kind of thing, start thinking, wow, these people could have an iodine deficiency. So you absorb it in the intestinal tract. You'll get rid of it pretty quickly, unless you suck it into the thyroid gland and use it. Otherwise, you'll pee it out in like a day. But your thyroid gland selectively pulls iodine into it. It has iodine trappers. They're secondary active transports that use sodium and iodine, and sodium iodine symport, it's called, NIS transporter, that takes iodine into the thyroid gland so you can make thyroid hormones with it. Here's your iodine trapping. And the iodine in your blood is in the form of iodides, so we can call it either iodine or iodide. But you use this NIS transporter, sodium iodine symport, as a co-transporter, and it pulls it in. TSH, one of the things TSH does is it turns these trappers on so you get more iodine. So thyroid stimulating hormone is going to stimulate the thyroid gland in a lot of ways, but one thing it does is it makes them pull in more iodine. One interesting thing about this is when you give somebody more iodine, they take more into their thyroid, up to a threshold. If there's too much iodine in the blood, your system shuts down to protect your thyroid gland, and it doesn't take in any more. And that's the logic behind people, when the nuclear reactors blew up in Japan and melted down, and we had radioactive iodine drifting across the ocean. That's what killed so many people in Chernobyl, was that all the radioactive iodine got in the soil, and then you either breathe it in or you eat vegetables that have radioactive iodine. It goes into your thyroid and kills your thyroid gland, or gives you thyroid cancer, one or the other. So you die of thyroid cancer, or you die from lack of iodine if you don't have proper treatment and stuff. So, but if you give somebody iodine supplements of good iodine and overwhelm the iodine, the thyroid gland, it'll stop taking in iodine. And that's why people in San Francisco and stuff were taking iodine supplements in case some of this radioactive iodine from Japan came over and they breathed it in, they would just pee it out and they wouldn't pull it into their thyroid glands. So we're going to form your T4, your thyroxine, and your T3. what you do is you bring in tyrosines into the cell, and you stick them end. So you have a whole bunch of tyrosines stuck together in this long pearl necklace, this long chain. And that is thyroglobulin, and that is what gets stored in the colloid. Then you start adding iodines all over it. You've got all these tyrosines, and you add iodines every place that you find a place. Then when you bring it back into the cell to cut it into twos so you can have your thyroxine, if it has 4 iodines on it, it's T4. If it has 3, it's T3. If it only has 2, it gets recycled and you use it again because it's not useful. So here we have TSH is stimulating your trappers here to bring in your components you need. For the THS receptor, it will stimulate everything in here. It even stimulates you to make more cells. If you need more thyroid hormone, you'll produce a lot of TSH. The TSH will stimulate your thyroid so much that your thyroid gland grows really big. So TSH stimulates the thyroid. So you take in your tyrosine, you take in iodine, you stick them together in these long strings of thyroglobulin. You start adding iodines onto the various sites. Then when you need it, you pull it back into the cell, you break it into twos. With your lysosomes, they digest it basically into twos, and your T3 and T4, mostly T4, remember, are released into the blood. And so that's how you make this. You pull in the components, you store it, you break it, you bring it back into the cell, break it into your right size pieces, recycle what didn't work at all, and release into the blood what you made, which is mostly T4. Now T4, like steroid hormones, is not water soluble. It's not exactly a lipid, so, people say, oh, well, it's not a lipid, but it acts like one. Okay, it doesn't dissolve in the plasma properly, and therefore it has to be transported in the plasma, bound to a plasma protein. Proteins are water-based, and they can dissolve in the plasma. So your steroids and your thyroid hormone, not TSH. That's not a thyroid hormone. That's thyroid stimulating hormone. Your thyroid hormones, T3 and T4, have to be transported in the blood bound to transporters, and so do steroid type hormones. As a result, they are slow to build up and slow to clear. It's not like adrenaline or an epinephrine, which goes into your blood instantly and you get this rush and then it's gone in no time. These, it takes a little while to bind them, it takes a little while to release, so they're slower to act and slower to clear. Then, here we are, it's bound to thyroid binding globulin. That's pretty good, right? TBG, thyroxine binding globulin, actually. And you've got T4 and T3, which, mostly T4. It's taken in by some transporters that pull in the T4 and T3 because it releases from the binder so it can go through. And because it's kind of lipid-based, some of it goes right on through anyway without even a transporter. Not exactly lipid-based, but enough. Some of it makes it across. Your T3 goes in and acts. Your T4, when it goes in, you convert most of it to T3 so it can act. This is a deiodinase. Look, it takes off an iodine. So T4 becomes T3. So you mostly make T4. It's bound, travels to the cell, lets go and goes through, converts it to T3, and then it goes inside the nucleus to have its effect. Your lipid-type hormones tend to act in the nucleus. They can go through membranes, and so they get inside the nucleus and act there. All of your water-based hormones act on the surface. Remember, they bind to G proteins or catalytic proteins if it's growth hormone or something like that. All the hormones that come out of the hypothalamus, all those releasing hormones and stuff, and all the hormones that come out of the pituitary are water-based. They are not lipids. They are not steroids, and they aren't thyroid hormone. So those are various stimulators, and those are all water-based. They act fairly quickly, and then they're gone fairly quickly. And then once you get to the target tissues, the thyroid gland, the adrenal gland, and the testes, and ovaries to some extent, you make more of the steroid-type hormones. Now here we have T4, a lot of it. We have actually two kinds of deiodinase. One that will make T3 when you need more thyroid action, and one that takes off a different iodine and makes it into RT3 if you don't need as much. Now this is kind of an interesting thing too, because, for instance, during fasting or famine, because you're starving to death, and thyroid hormone is everything to do with metabolism, you start converting a lot of your T4 into RT3 to lower your metabolic rate. If you go on a crash diet, you'll start converting your T4 to RT3 and your metabolic rate will drop, and it makes it hard to lose any more weight. In Western society, the main culprit for starvation is anorexia or bulimia, where you intentionally eat so little to try to get skinny, and you wind up producing so much RT3 that you become hypothyroid along with it, along with the fasting or malnutrition. In other countries, it happens a lot, in countries where they're having famine or a drought or something like that, and they truly can't get enough calories to keep their thyroxine converting the way it normally would. Mechanism of action. Remember, it came with its binding globulin. It released and came through. It converted into to T3 mostly, and then it actually binds right on the genome. T4 and T3 bind to your DNA strands and cause you to make proteins, gene transcription. You make stuff. You make sodium-potassium pumps. That's one thing that increases your metabolism so much. Sodium-potassium pumps at rest are 80% of your metabolic rate, pumping those ions around and using ATP in the process. So you make a ton of sodium-potassium pumps, and it raises your metabolic rate way up. Gluconeogenesis, it turns those systems on, respiratory enzymes, so that you increase the utilization of nutrients. Makes beta adrenergic receptors. Where have we seen that? Beta receptors on the heart. You think that would increase your heart rate? If you had more sympathetic receptors on the SA node, your heart speeds up. More sympathetic receptors on your heart muscle, it squeezes harder. So all of these things that have to do with metabolic rate increase due to the action on the genome that causes you to make those extra proteins. Mainly metabolic. Increase your basal metabolic rate by twice, by double. Somebody who's hyperthyroid is usually really skinny. They burn off their calories really fast. A lot of ATPase pumps. Increased utilization of nutrients. So you burn them, you convert them, everything speeds up. Growth is increased if you're a kid. Okay, well, this is okay to, you'd think, well, growing is good. But what it does is it speeds up the process. So a hyperthyroid kid might be tall for his age, but then the epiphyseal plates seal early, and he stops growing. an iodine deficiency. If you have an iodine deficiency, you can't grow as much. So a kid that is hyperthyroid might grow fast for a little while and then stop. Iodine deficiency, it's like that panhypopituitarism kid where there's not enough thyroid hormone to allow for the growth process to take place properly. And one of the big problems it has is growth of the brain. So people in serious iodine deficiency can have mental retardation. And the negative feedback is both long and short loop. So here the TRH from the hypothalamus makes you release TSH, water-based. It goes into the blood, turns on the thyroid gland, which makes mostly T4, a little bit of T3. Okay, the T4 and T4, a lot of that converts to T3 by losing an iodine. And then it has all kinds of effects. And the negative feedback is primarily T4, because that's mostly what's in your blood. So it will, if you have plenty of T4, it'll turn off here and here, your negative feedback. So if you have hyperthyroidism, if you have a tumor here that's making too much thyroxine, how much TSH are you going to make? Less. Because the negative feedback is so strong, you don't want more. So if T4 is high, you'll turn these guys off and TSH will go down. They do a lot of testing for thyroid problems by testing TSH because it's easy to test for. If TSH is low, they assume you're hyperthyroid because that's what's keeping it low. If it's too high, they assume you're hypothyroid because there's not enough negative feedback and you're producing too much TSH. This hopefully will become clear in the lab this week, which has rats that we are testing for their metabolic rate. We're injecting them with thyroxine, T4. We're injecting them with TSH to see what happens. And we're injecting them with a thyroid inhibitor to prevent them from making enough T4 to see what happens to said rats. Virtual rats. So, knowing what thyroid hormone does, you can imagine what too much of it would look like. A toxic amount of something, like if you drink too much alcohol, you have toxic levels. That means too much. So, thyrotoxicosis, a condition of too much thyroid hormone, all you have to do is look and see if your T4 is too high. On a list, all you got to do. If your T4 is too high, that means you have too much T4. That's thyrotoxicosis. It's also called hyperthyroidism. Generally low TSH. You can treat it either with radioactive iodide, an amount that will kill the thyroid gland, or surgery. The dean of my medical school said if you talk to a surgeon, they'll want to use surgery. You talk to a radiologist, they'll want to use radioactive iodine. He thinks that with surgery, you can remove part of it, leave part of it, and maybe solve it without having them spend the rest of their life on thyroid drugs. But if they have thyroid cancer, you have to remove it, and that's just the way it is. So if they have an adenoma or a tumor, adenoma means a gland tumor, then you can remove the tumor or burn it out. Ablation just means to get rid of something. So ablation, you can freeze it or burn it out or cut it out. Hypothyroidism means you don't have enough thyroid hormone. So if T4 is low, TSH will probably be high, right? Because it's trying to make more. But if T4 is low, you have hypothyroidism. There are two basic kinds. One is just your thyroid gland isn't working properly. It's called idiopathic. Idiopathic means we don't know what's causing it. It's just not working right. So you can have an idiopathic hypothyroidism, or you can have an endemic goiter. Endemic means it's localized to an area, like West Nile virus is endemic to the Caribbean. If you have a whole town where everybody's got a swollen neck, that's an iodine deficiency. Not everybody has some, by some miracle has the same thyroid issue. Instead, they don't have enough iodine in their diet. The T4 goes down because they can't make it. They don't have any iodine. As a result, the TSH goes sky high, trying to make more. What does TSH do? It stimulates your thyroid gland to, among other things, grow. So, hypothyroidism, endemic goiter, iodine deficiency, a group of people who all have the same dietary deficiency will all have a tendency to create these goiters. And, high T4 with low TH is usually hyperthyroidism. Low TH, T4 with high TH is usually hypothyroidism. But this is, if it's high T4, it's hyperthyroidism. It's low T4, it's hypothyroidism. Now, you might need to do specific tests for T3 and RT3. Because if the person is making the normal amount of T4, you'll say, well, it doesn't look like hyperthyroid. But what if they're starving themselves to death and therefore converting all their T4 into RT3? Then they will appear to have hypothyroidism because they're not making real thyroid hormone. They're making the fake stuff. Signs and symptoms: hypothyroidism, low basal metabolic rate, everything slows down, speech, mental acuity, you gain weight because you can't burn it off, your metabolism's low, so you're not making enough heat, so they're cold all the time. They're not using up their nutrients, so their cholesterol and triglycerides go up, and they likely will have a goiter produced because they're not making enough thyroid hormones, so they make too much TSH. Hyperthyroidism, the opposite. Increased heart rate and temperature. I'm hot all the time. Increased fuel utilization, so they're skinny, they're weight loss. Agitation, tremors. Low blood lipids. Muscle cramping. You're using up the nutrients. You're overstimulating the tissues to be extra active. Now, it does increase your mental activity, but not in a way that's good. Students said, well, why shouldn't I take thyroid hormone before a test? Well, if you want to take your test like this, then maybe that would be a great idea, but probably not. One other thing is this bulging of the eyes. It's actually that the eyelids withdraw, and a typical person with serious hyperthyroidism will have this exophthalmos, it's called, like this. She has hyperthyroidism. She's skinny, bulging eyes, hypothyroidism, perhaps mental retardation, lack of growth. It looks kind of like dwarfism, but it's partly a lack of growth, but partly a lack of mental stimulation and development. There's the goiter that is developing. If you don't have enough iodine, you can't make enough T4, so there's no negative feedback. So that you make tons of TRH, tons of TSH to try to stimulate the thyroid gland to make more T4. But there's no negative feedback, so you keep making more and more and more. You can't make enough T4, and your throat starts to bulge. And here we have a kid fairly early in life is already developing a goiter. This is in central India, a long way from the ocean, a severe goiter. Now, if you treat them with with iodine, if you supplement them with iodine, these goiters will reduce. His probably will go away completely. Hers I wouldn't bet on it being gone forever, but it would certainly reduce. Summary slide. Da-da-da-da-da-da. Here you have stimulation, trapping, T3. Okay, a good slide to just kind of go through and make sure that you understand all of those concepts. And now, another anterior pituitary hormone is going to go to your adrenal cortex. Adrenal. Okay, renal means kidney, adrenal. On top of the kidney, you have your adrenal glands, and the cortex, or the outer layer of the adrenal gland, makes a bunch of glucocorticoids and things. Now, the central part, the adrenal medulla, makes epinephrine and norepinephrine. All right, that's your stimulation by the sympathetic nervous system. We talked about that when we were talking about the nervous system and stuff. So, you know, epinephrine and norepinephrine released from the adrenal glands as part of the sympathetic nervous system. What we're going to look now is the adrenal cortex, where you're making a small amount of steroids. You actually make a little testosterone and stuff. But you also make these other steroid type hormones, which are the mineralocorticoids, aldosterone, and glucocorticoids, mainly cortisol. Okay, once again, a reminder, epinephrine and norepinephrine from the renal medulla. Okay, great. However, the renal cortex, adrenal cortex, that should say adrenal cortex. Oops, not renal cortex, adrenal cortex, it should say. Nope, I can't. It won't let me do it. Okay, too bad. Adrenal cortex. Adrenal, steroid hormones. Each layer produces a different kind of hormones, aldosterone, and then cortisol, and then some steroids. I don't care if you know which layer does which. I just want you to know what they do and know that they come from a layer of the adrenal cortex. The main one we're going to talk about coming from the adrenal cortex is cortisol. Cortisol. It's the big one. It is your main stress hormone. Now, epinephrine and norepinephrine are instant stress. Somebody points a gun at you and you get a fight or flight instant stress. It does, it causes a response to stress. But long-term response to stress is through cortisol. So you're making some cortisol while you're studying for tests and going to class and trying to raise your family and hold down a job at the same time. Stress will cause you to make cortisol to help you deal with the stress. It is a steroid, like cortisol. Cortisol, hydrocortisone is cortisol. You put on your arm if you get an ant bite to reduce the inflammation. It's an inflammation reducer. Okay, it contains the reactions. Lipid base, so it has to be transported by a carrier protein. Cortisol binding globulin. That's nice that it's named that. Cortisol binding globulin. So it's released from the adrenal cortex. It binds to cortisol binding globulin. The important thing about knowing that it has to be bound is you can have a deficiency in these binding proteins that could make you hypo something by themselves. Okay, so it's bound, it's released, it's a steroid, so it's lipid-based. It goes through and it goes into the nucleus and has its effects. Okay? See, we didn't have to spend as much time on this one. You make your steroid hormone, it binds, it goes through the bloodstream bound, and then it releases, it goes inside, it goes into the nuclear membrane, it binds here, and makes you make proteins. It will take proteins from the body and use them to make more glucose. So in times of starvation, you're able to make enough glucose to keep your brain alive because your brain can only eat glucose. It increases the ability to mobilize and utilize whatever stored nutrients you have. It allows the body to survive during famine or other types of stress. But long periods of overproduction will cause your muscles to reduce in size and your fat deposits to increase because you're converting more of your muscle into other nutrients and depositing it at places. Now, what you want, of course, is exactly the right amount of cortisol to make sure that everything works right. What you don't want is too much or too little. Releases fats into the bloodstreams while sparing some carbohydrate. Some of this fat is redeposited in the trunk and face. It's called the buffalo hump. It will increase abdominal fat. It gives you what they call the moon face. This is before and after treatment for Cushing's. It's Cushing's disease is the name for hypocortisol, or hypercortisol, I'm sorry. Too much cortisol. Too much cortisol causes you to redeposit all of this fat where it's not supposed to be. Stretch marks and all. Okay? Here we have somebody with, again, he's deposited fat on the trunk. His legs are getting skinny from lack of muscle mass. The muscle is being converted into sugar and then being stored as fat. Here's his buffalo hump. Cushing's disease is too much cortisol. They both start with a C. Cortisol decreases the inflammatory response to injury. So it keeps us from overacting and causing ourselves too much inflammation. So if you have a cortisol deficiency, you're likely to have too great an inflammatory response, more likely to have an autoimmune type reaction to a normal amount of invader. If you have too much cortisol, not only you get Cushing's with the buffalo hump and all that, but it can suppress your immune response so that you get sick easier. You need enough immune response, you just don't need too much. Regulation has a long loop and short loop. So CRH causes ACTH to be released from the pituitary. It goes to the adrenal cortex, causes you to make cortisol. Cortisol is your negative feedback. It goes back to the pituitary and hypothalamus to say enough is enough. Another hormone that comes from the adrenal cortex, we won't spend as much time with it now because this is an important one with the kidney. So we'll see this in the kidney thing because it's another hormone that causes you to retain or lose water. Retain water mainly at the kidney. So it's big, it's super important in regulating your blood volume and blood pressure. Remember the renin-angiotensin-aldosterone system? Well, if you have low blood pressure, your kidneys release renin, produces angiotensin 1, converts to angiotensin 2, goes to the kidney, the adrenal cortex, and causes you to make aldosterone. Aldosterone acts at the kidney to make you absorb more sodium and therefore absorb more water, and your blood pressure goes back up. So you should remember that from the blood pressure lectures. So aldosterone, a big deal, and big deal with blood pressure and also big deal with kidneys. Aldosterone, negative feedback, it's mainly long loop back to the hypothalamus. Okay? If you have enough aldosterone, you stop stimulating your adrenal cortex. Also, one of your main negative feedbacks comes from your blood pressure change. Okay? Because if your blood pressure goes back up, you stop making renin. and angiotensin II, and then you stop making as much aldosterone. Too much aldosterone, your blood pressure goes too high. What does aldosterone do? It raises your blood pressure with the renin-angiotensin-aldosterone system. You're likely to have too much aldosterone and too much sodium because you're retaining sodium and you're retaining water. But you're likely to have too little potassium because you retain sodium by running sodium-potassium pumps faster. So you're pumping sodium back into the blood, but you're pumping potassium into your pee. So hyperaldosterone means hypertension, but perhaps hypokalemia, not enough potassium. Hypoaldosterone, hypotension, and hyperkalemia. And here's a summary slide for the adrenal hormones. There's a lot of things to remember, but think about this. Be able to walk through it. Okay, we're talking thyroid hormones. So thyroid releasing hormone from the hypothalamus causes thyroid stimulating hormone to release from the pituitary. It goes to the thyroid gland and stimulates it to take in the products it needs, including iodine, store them, break them back up, and release them as T3 and T4. The T4 travels by a transporter, goes into the cell, most of it converts to T3, acts on the nucleus, increases metabolism. Okay? If you can walk through that, you're going to get the questions right on the test. Cortisol, CRH, causes ACTH to be released from the pituitary. It goes to the adrenal cortex. You release cortisol. Cortisol lowers your immune response. Okay, it also can cause Cushing's if you have too much of it. What you want is just exactly the right amount. Negative feedback is cortisol. Okay, so be able to do that on these various different hormones, and it's going to get you a long way on these tests. Okay, that's it. And I hope you got this whole lecture.